When you can you see my web page now?
Yes.
So you go to module 1, right? So the PowerPoint slides are the one I'm going through today. Slide handout is for chapter 1 is for printing if you needed to print out. Now I have put the video of the Zoom class meeting for last Thursday, August 19. You can go back and watch if you haven't been to the class. So you also need to be doing quiz 1 for chapter 1 after we finish chapter 1. All right, so keep that in mind. I will get the gradebook organized and you will see the points that you are making right now. Right now,
I have a question.
Yes.
Where is the video located? Where can I find that?
Can you see the web page now?
Yes. Oh, okay.
CHEM-105, chapter 1, August.
Video. Okay, got it. I see it.
So I'm going to add the second one after that, okay? Today's class.
Okay, thank you.
So you can also go down and chapter 1 question and answers. Just practice some problems and see whether if you can get the answer, all right? Okay, I'm going back to chapter 1 now. I'm trying to get rid of the names of the people here that appear in the... Okay, anyway, I will worry about it later. Okay, I'm going to chapter 1 now. So can you see my chapter 1?
Yes.
Okay, good. Now we have, let me review a little bit because we don't want to jump into it. We were going over material. I think slide 41 or something, I will go there. Last slide we cover. We study classification of matter in this chapter briefly, and scientific method, and reporting numbers in science, significant figures, how you make measurement in lab, and we describe the states of matter, unit conversions, converting temperature from one scale to another. We talked about several equations. So we are at the point where we were about to define specific gravity and use density calculation to obtain volume or mass of a substance. And today we're going to focus on items 12 and 13. 13 is describing forms of energy. Let me go to the specific gravity. Specific gravity, as we talked in the previous slide here, is the density of substance divided by density of water. Therefore, specific gravity is unitless. So when you, it's same as density, water having 1.0 grams per milliliter density. So specific gravity is another name, form of expressing density of water. For example, what is the specific gravity? Let me put that away from here. For example, density of copper is 8.92. How do you get the density converted to specific gravity? Density of the material divided by density of water, which is at room temperature 1.00 grams per milliliter. So it's 8.92 without units. So we identify material by density so many ways using physical properties, melting point, etc. Density and specific gravity is one of the physical properties of certain compounds or elements. Now we are going to go into various forms of energy. Energy can be described as kinetic energy. A matter, when it moves, it has certain energy that is known as kinetic energy, energy of movement. Potential energy is where it's, depend on where it is stored. For example, potential energy of a boulder or the rock on the top of a hill is much higher than bottom of the hill. That when you change the position, that amount of energy is released as potential energy. Waterfall turns turbine to produce electricity. So that stored energy is converted to electrical energy. So these are basic description of energy in matter, either kinetic or potential energy. Potential energy comes from moving. Kinetic energy comes from moving. Potential energy comes from the way the object is arranged or placed. For example, kinetic energy is thermal energy, which depend on particle movement. As the temperature increases, the thermal energy increase. The particles in the matter, which are atoms and molecules, move faster. Mechanical energy is when kinetic energy is converted to useful form of energy. That's called mechanical energy. Energy produced from motion is mechanical energy. Electrical energy is moving electrons through a wire. You produce electrical energy. That's form of kinetic energy. Magnetic energy also produce rotations in generators, motors, rotation in motors, where electrical energy is converted to magnetic, then push or pull in the magnetic field drives the motor. Those are forms of kinetic energy. In atoms and molecules, potential energy is stored in chemical bonds. Energy is stored in food as chemical bonds, fuel. When you burn fuel or gasoline, you convert that chemical energy to different chemical bonds, releasing energy. So elastic object like rubber strip has certain energy, which is when it's stretched, it releases that energy. Also, nuclear energy stored in the nuclei of atomic subatomic particle called nucleus of atom is very large amount of energy. It's released when an atom get converted to different elements. The mass is converted directly into nuclear energy. So that's very strong force of energy, store of energy. So gravitation also produce energy because of different objects in different places in the gravitational field. So higher gravity moving object from on the top of the mountain to bottom of the mountain produce energy as a form of gravitational energy. All these forms of energy are felt by us as heat. Heat energy is something that we can feel. So we use to cook food, stay warm, and we also hear some of those all forms of energy could be converted to sound energy or light. Some of they produce heat directly, light directly, or electricity that is converted to sound, etc. All forms of energy could be converted to each other. That's one of the thing about energy. Energy is conserved during the process. As we described in the previous slide, two main forms of energy is kinetic energy and potential energy. Energy is defined as capacity to do work. Kinetic energy increases as object's velocity increases. It's given by half mass times velocity squared, half mv squared. Potential energy can be an object has because of its position stored energy. For larger objects like rocks and boulders, that's directly the height from the Earth surface increase potential energy. In molecules and atoms, especially molecules, potential energy is stored as bonds. So bonds broken could release that potential energy. So basically two forms of energy, two main forms of energy, kinetic energy and potential energy. Kinetic energy, we are still describing that diagram, previous diagram we went over a couple of slides ago. Example of kinetic energy are mechanical energy, heat energy, and electrical energy. These are main forms of energies that we use derived from kinetic energy. In chemistry, most important forms of potential energy are chemical energy and nuclear energy. Chemical energy is stored in chemical substance as in, for example, as in food such as carbohydrates, fats, and oils. They are stored in chemical bonds. When they break, they produce energy for our metabolic functions. It is given off when substances take part in chemical reaction. When they do undergo a chemical reaction, the bonds are broken, releasing energy. And exothermic reaction, endothermic reaction can take place during chemical reactions. One of the important thing about energy is they follow law of conservation of energy. That energy is neither created nor destroyed. So that's one of the fundamental principles of energy. Like law of conservation of mass for chemical reactions, law of conservation of energy is key idea in energy. Energy can be converted from one form to the another. When you convert energy, sometime along with when you burn coal, part of it is used to heat water as heat, as kinetic steam energy to run turbines. Part of it is released as heat, but together mechanical energy and the heat energy is equal to the energy produced by burning coal. That energy is neither created nor destroyed, but they can convert one form to the another. Forms of energy is heat. Heat energy is related to temperature because heat is related to kinetic energy of the particles making up the matter. Heat transfer takes place when two objects with different temperatures are brought together. So hot object, you understand when some object is hotter than the other one, when they brought into contact, they transfer in heat energy. That's kinetic energy, movement of particles in the hot body is faster than the cooler object. So all particles becomes moving at same kinetic energy. Thermal equilibrium is reached and two bodies are at the same temperature. Heat is measured in calories. Calorie is the heat required to raise the temperature of 1 gram of liquid water by 1 degree Celsius. Calorie is not the unit of heat in the SI system. SI units or science metric units. Unit of heat is joule, which is about 1/4 of a calorie. So it's 4.184 joules, 1 calorie. So you use conversion factor to convert calories to joules. Density. Specific heat is of a substance is a physical property. Specific heat is defined as heat required to raise the temperature of a 1 gram of substance by 1 degree Celsius. So specific heat of water is 1. This happened to be pretty coincident. what is the density of water? Is one. Maybe water is the most common thing we have. We use that as a unit. And relative to that, we measure other stuff. Specific heat of ice is different because it depends on physical state. Steam is same as ice. Iron is 1.11, 0.11, aluminum 0.22. If you look at this table of specific heat, water has the highest specific heat. So that means water can store more energy, more thermal energy when the temperature is increased. So in a hot summer days, large amount of heat absorbed by oceans. As the temperature go up in the atmosphere, a lot of heat is absorbed. Therefore, that large amount of heat can be released at night to maintain the thermal balance. That means there's no sudden fluctuation of temperatures. Heat is absorbed, heat is released, maintaining a comfortable temperature on the surface of Earth for well-being of biological organisms. So you can compare two specific heat and say which one has more heat capacity. More heat is required to increase the temperature. Now you need to calculate heat absorbed by or released by certain object or matter. The following equation is used to calculate the amount of heat absorbed by certain object. It's specific heat times mass times change in temperature. Final minus initial temperature. T2 is final, T1 is initial. So if somebody asks you what is heat absorbed by water, 10 grams of water, by increasing 40 to 60 degrees Celsius, you can plug in and calculate. How many calories are required to heat 352 grams of water from 23 to 95? The specific of water is given. So that is 1 times 352 times 95 minus 23. That's negative calories. Why? Okay, heat absorbed is positive calories, is heat absorbed. If the temperature was to decrease from 95 to 23, that's a release. So it's a negative. So that negative sign take care of heat absorbed or heat release. Heat release has negative calories, indicating the release of heat. So this equation could be used in calculations. So we have finished the material that we need to cover in chapter 1. We covered classification of matter, measurement, and energy. Do you have any questions from these slides we went over today? Please read them carefully and go through sample questions and see what question could be asked from this material for chapter 1. So I'm going to move on to chapter 2. Let me share my slides. In chapter 2, we're going to cover details of atoms. We got the idea that matter is made out of atoms and molecules. Molecules are more than one atom. When combined into a unit, it's called a molecule. So we're going to use the idea of atoms in classifying matter. We're going to look into Dalton atomic theory in detail. Then we're going to look into structure of the atom, the composition, nucleus, and electrons. Nucleus is composed of neutrons and protons. We arrange atoms in the form of elements in a table called periodic table. Periodic table is an arrangement of elements using atomic number and chemical properties. So we're going to describe the periodic table. The periodic table shows chemical properties. Chemical properties depend on electrons, arrangement of electrons in an atom. Excuse me. Therefore, to understand electrons, arrangement of electrons in an atom is important. So we came up with the idea an atom has electron configuration where it describes the arrangement of electrons in atomic orbitals and its relation to periodic table. We're going into details soon. Periodic table also shows certain properties like atomic size, ionization energy, and number of charges found on ions. So we could use the periodic table to get quick answers to certain properties, how they change in the periodic table. Anyway, we're going to go over this again with this idea expanded. The classification is based on pure substances, which are elements and compounds, and mixtures are complex substances. We will describe the basic parts of an atom, basic features of periodic table, how the element symbol is used in the periodic table, and how we classify elements into groups of metals, non-metals, metalloids, etc. We're also going to learn about the different atoms called isotopes of an element and how the atomic weight is calculated in the periodic table based on isotopes. We will understand the electronic structure of atom, electronic configuration. Write an electronic configuration for an element using periodic table. Relate location of periodic table to electronic configuration. We also look into what we call valence electrons, which are the outermost electrons in an atom. And we, based on valence electron, we write down electron dot symbol for an atom. These are used for bonding descriptions later. Therefore, we're going to learn more about electron dot symbol for atoms or elements. So we will predict the variation of atomic properties, size and ionization energy in the periodic table. So let's go ahead and do this. One thing you're going to learn in chemistry is ordinary things are made up of chemicals. Even though it doesn't look like food is a chemical, but it's complex mixtures of carbohydrates, which are chemicals in a true sense. You don't feel like you are eating chemicals, but all chemicals are not harmful. But when they are in high concentration, they could be toxic. There's nothing you can hold or touch that is not made out of chemical. Chemicals make up virtually everything we come into contact with. Our air, water, everything in the house, food we eat are made out of chemicals. You don't like the idea, I know. Chemicals are, you are not eating chemicals. There's a kind of a fear that chemicals are always causing bad things, like carcinogenic, but it depends on the chemical and dose or the concentration you are exposed to. The idea, all things are made out of atoms, molecules, and ions, are considered, idea is considered the most important in all human knowledge. So according to Richard Feynman, Nobel Prize winning physicist, he came up with the statement, all things are made out of atoms, is the most important idea in all human knowledge. So we can use chemistry and physics. So of course, all the sciences use atoms and molecules. Chemistry is not a standalone subject area. It is in our descriptions. It's like mathematics is in everywhere. Physics is also. Engineering is application of, and medicine are application of sciences. So how we came with the idea all things are made out of atoms, molecules, and ions? This idea was developed throughout the history and culminated in Dalton's atomic theory. All matter is made out of atoms. Is an idea that Dalton atomic theory proposed. So, like we describe in scientific method, a theory does not start from the thought. Theory starts from experiments, observations. So matter can neither created nor destroyed. Mass of matter can be neither created nor destroyed. It's called law of conservation of mass, developed by Lavoisier. So Dalton explained, if matter is made out of indestructible atoms, then any chemical reaction must change the attachment among the atom, but does not destroy the atoms themselves. For example, carbon monoxide reacting with lead oxide go to carbon dioxide and lead. This is easy to explain based on atomic view. So idea of atom is very useful. So to describe Law's conservation of mass, Dalton proposed his theory. Also law of constant proportion. In a given chemical compound, for example, hydrogen and oxygen, produce, that arrow should be after oxygen. Hydrogen and oxygen produce water. So the amount of material present in 36 grams of water is always 4 grams of hydrogen and 32 grams of oxygen. Mass is conserved. So, but atoms combine in constant proportion by weight. It indicates the presence of atomic structure in the matter. Also, there was a law called law of multiple proportions. When two different elements combine in whole number multiple ratios, they form two different compounds. For example, carbon monoxide and carbon dioxide. The amount of oxygen in two compounds, in carbon dioxide twice as many in compared to carbon monoxide. There's 1 to 2 multiple proportions. Multiple means 1 times 2 is a multiple of 2, whole number ratio. That means these are two distinct molecules with chemical properties, different chemical properties. That shows atoms are there. And this can only be explained in terms of matter having basic units called atoms. Different kind of atoms are there called elements. John Dalton came up with the following statements called postulates of Dalton's atomic theory. All matter is composed of very tiny particles, which they call Dalton called atoms. Idea about atom was present in Greek philosophy also. Atomos came from ultimate particle, atoms, a Greek word. All atoms of the same element have same chemical properties that define an element. Atoms of different elements have different chemical properties. Same element have same properties. Different elements have different chemical properties. To explain law of multiple proportion, Dalton came with the idea compounds are made from chemical combination of 2 or more of the same or different kind of atoms. Compound is a molecule or ionic compound, sodium chloride. So it has two different kinds of atoms. Molecules are tightly bound combination of two or more atoms that act as a single unit. So molecule is a group of atoms bonded to each other. So Dalton's theory, or using these using the postulates, these postulates describe the atomic theory to explain. Atomic view of matter. There are monoatomic particles. That means only one kind of atom. Example is noble gases, helium, neon, argon, krypton, etc. The elements occur as diatomic molecules. So they are still elemental, but they have diatomic molecules, hydrogen, nitrogen, all these gases have two atoms. There are also polyatomic elements, like ozone has more than two is poly. Phosphorus, sulfur has 4 and 8 atoms. Diamond is a group of millions of carbon atoms bonded to each other to form a gigantic cluster. Diamond is the hardest substance on Earth because they are bonded to each other strongly. The gems have network covalent bonds. That means they spread out, covalent bonds spread out throughout the space, throughout the crystal. They are harder material. So we're going to look into use this idea about matter is composed of atoms right throughout our chemistry. When we look at matter, there's a macroscopic view or ordinary view, like this Coke glass, soft drink glass with dark brown liquid. That's how we see it, bubbles passing and released on the surface of the water. But in a molecular view or atomic view, we can imagine there are water molecules, carbon dioxide molecules, and sugar molecules dissolved in together to form a solution. On the tip of the carbon tip of the pencil, there are carbon atoms which are in the form of graphite, that when we write down on the paper, that graphite is transferred to the paper, showing our writing. On the hand of a person writing with the pencil, hand is composed of proteins. Proteins are amino acids. So they are complex structures. This is a giant molecule of proteins. So everything is made out of atoms and molecules. And that we're going to use throughout the chemistry. To expand on this idea, the matter is composed of pure substances and mixtures. Pure substance is an element or a compound. Elements combine chemically to produce compounds. The mixtures are mixtures of several types of pure substances. They are complex mixtures. They contain more pure substances. Mixtures could be heterogeneous or homogeneous. So that's a basic classification of pure, the classification of matter. So this is, when you say pure substance, is either element or a compound. They have fixed chemical properties. Mixtures are mixtures of pure substances, either element with a different element or compound with a compound with another different compound, or element and another compound. It could be more than two. So therefore they are very complex. Homogeneous means the composition is uniform throughout. That means every part of the sample, like in a solution, salt solution, composition is same. Heterogeneous means is different phases are present. Different phases means different particles with different composition are present in the, like in a garbage can, or like a piece of cookies. A cookie has heterogeneous nature. One part you have chocolate, one part you have the bread, brown bread part, and different parts have different composition. So we're going to look into atomic view of these. Element is a substance. Example, carbon, hydrogen, iron are consist of identical atoms. We're going to look into details of atoms, atomic structure in a few slides. There are 118 known elements. In the periodic table, if you have seen a periodic table, it has so many elements. Some are stable, some are radioactive that are breaking apart. Some are already decayed radioactive elements. Some are producing nuclear reactions. Out of these 118, 98 occur in nature. So 98 are either stable. I think about 83 are stable, and others are 98 of 82 are stable. So about 16 are unstable, radioactive. They decay to other elements. Some new ones are made by chemists and physicists using high energy particle collisions in nuclear reactors. Most of these atoms have atomic symbols, 1 or 2 letters, just like carbon has 1 letter, big C. First letter is capitalized in the carbon. That's the symbol for carbon. Hydrogen, H. Iron is Fe. Fe comes from Latin word ferrum, Fe. So certain elements have, other than English name, letters from English name. So English name of the element, people important to atomic science, geography, location, planet, etc. are used in English name or variety of German and Latin names are used. Potassium is K, kalium, Latin word for potassium. So we're going to look into, you can check through the periodic table for different names for elements starting with elements having symbols other than English name. A compound is a pure substance that's made out of 2 or more elements in a fixed ratio by mass. So fixed ratio, CO, CO2, like multiple proportion, law. Formula of a compound tells us the ratio of its constituent elements and identify each element by its atomic symbol. Sodium chloride has one sodium ion and chloride ion. It's an ionic compound. The ratio of the sodium ion to chloride ions is 1:1. Compounds could be covalent compound or ionic compound. Water is a covalent compound with 2 hydrogen atoms bonded to oxygen. We use different representation to indicate in our discussions about the structure of molecules. We take water as an example. Water formula is, molecular formula is H2O. 2 indicate there are 2 hydrogen atoms. Structural formula is showing bonds. When formula is showing bonds, there are 2 chemical bonds, covalent bonds, connecting oxygen to hydrogen. There are also You guys have a question? Okay. The other representation is called ball and stick models. Sometimes we show pictorially different colors to show different atoms. Red atom is oxygen. The gray atom is, small gray atom is, they are according to size of atoms, based on size of atoms. There's a space filling model. We take up the electron clouds, the electron cloud of the atom and how they are bonded to the other different atoms with their electron clouds. So that's called space film models are electron clouds. So they are more real than all these three: molecular formula, structural formula, and ball and stick model. So sometimes we show that different representations. A mixture is a combination of two or more pure substances. And substance may be present in many mass ratios, different mass ratios. There's no fixed composition of pure substances. You can mix up any amount of sodium chloride, different amounts, to water and produce mixtures with different compositions. Each substance has different set of physical properties. Mixtures cannot be homogeneous, can be or heterogeneous. Homogeneous is when the mixture particles of the atoms, molecule, elements, compounds making up the homogeneous mixture are mixed thoroughly, like in a water solution. They're called homogeneous. Heterogeneous is when things are not mixed well. There are certain regions of the mixture composition is different, is called heterogeneous. If we know the physical properties of individual component of the mixture, we can use appropriate physical means to separate mixture into component parts. For example, if you have salt water comes from ocean. How do you separate salt from the water? You pump salt into a containers next to ocean, large sand lakes made out of sand, and you pump the salt water and let it evaporate with the heat from the sun. As the heat removes water, the sodium chloride crystallizes, and later you can, when the water is gone, you can break away the salts. So if we know the physical property of water, in this case, we know we can use sun heat to evaporate. Or in a lab, we can distill or evaporate in a beaker, leaving the salt. Now we're going to go into more details about atoms. Like we said in previous slides, atoms are smallest particles that can participate in chemical bonding, are the smallest particles in matter that take part in chemical reactions. But atoms are not indivisible. They have subatomic particles. When Dalton came up with his atomic theory, he thought atoms are indivisible. Ultimate particle, that's what atomos means in Greek. But we found out that atom has subatomic particles. If you think of an atom, it can be like solar system analogy, not exact analogy. Nucleus is the sun, planet rotating around the electrons. So that's kind of a nuclear model of atom. Protons and neutrons are in the nucleus. The protons have one positive charge, neutrons has zero charge, neutral. Electron has equal but negative charge to that of a proton. Mass of a electron is 1,000 times less than the mass of a proton, 10 to the negative 4. Mass of a proton and electron are almost equal, but neutron has some slightly larger mass, 1.0087. Reason for that we can explain now. Neutron could be formed by capturing proton and electron. Proton plus electron become that might be the small heaviness in a neutron is coming from a captured electron by a proton. Protons are in the nucleus, neutrons are in the nucleus, electrons are outside. We think planetary model for atom, which is we're going to say is not a same as solar system with the nucleus being the center of the atom and electrons moving around like planets. It's not a correct model. Electrons in an atom behave as waves. We're going to look at wave shapes, which are called atomic orbitals later. Relative size of atom, nucleus, and atom. Atom is about 10 to the 10 meters. Negative 10 meters. 10 to the negative 10 meters is the size of an atom. Then 10 to the negative 14 is the size of a nucleus. Nucleus has a higher density. Most of the mass is in the nucleus. There are a lot of space that electron occupies around the atom. Therefore, mostly mass is within the nucleus. The electrons contribute very little mass to the mass of the atom. So we write down atomic symbols, like I said, first letter of the English name or the first and second letter in small case, like cobalt. Cobalt is CO because carbon use C already, it has to come up with a different symbol. Mass number of an atom is the number of protons added together, sum of the number of protons and neutrons in the nucleus of an atom. Mainly protons and neutrons determine the mass of the atom. Atomic number is the number of protons in the nucleus. Protons number is also atomic number. It is also same as number of electrons in a neutral atom. So for example, we write down symbols, expanded atomic symbol, 12 as a superscript, 6 as a subscript. 6 is the atomic number, 12 is the mass number. Therefore, 6 protons from the atomic number 6. 12 is the sum of 6 plus 6 protons and neutrons. This in a written form, this isotope is called, this symbol is called carbon 12. We write the name of the element and the mass number, carbon 12. It's an isotope. For carbon also has carbon 13, atomic number is the same. Carbon 13 has 6 protons and 7 neutrons. So atomic symbol could be written for the element, just a plain letter symbol, or isotopic symbol showing the mass number and the atomic number. Isotopes are atoms of the same element which have same number of protons. An element is decided by number of protons in the nucleus. Carbon always has 6 protons, but they can have different number of neutrons. Carbon 12 has 6 protons and 6 neutrons. Carbon 13 has 6 protons and 7 neutrons. Carbon 14, which is a radioactive, has 6 protons and 8 neutrons. Most elements found in the periodic table found on Earth are mixtures of isotopes. For example, chlorine is chlorine 35 and chlorine 37. Chlorine 35 had 18 neutrons. And chlorine is atomic number is 17. Chlorine 37 has 20 neutrons. So 37 minus 20 is 17. But these two isotopes are in the ratio of 75%, 75.77%, and 24.223%. Therefore, we had to calculate atomic mass, average atomic mass, based on isotopes. The atomic number, atomic mass reported in the periodic table is the weight average of masses based on naturally occurring isotope of an element. So how do you calculate the average atomic mass? There are 2 isotopes. Isotopic mass is 34.97, which is the 35, chlorine 35. Isotopic mass is coming from experiments. You can calculate the isotopic mass. Chlorine 37 is isotopic mass is 36.97. It's very close to whole number, but there are specific numbers multiplied by abundance, chlorine is 75, chlorine 35 is 75.77 divided by 100 multiplied by isotopic mass plus abundance of chlorine 37 divided by 100 multiplied by isotopic mass. So we get the answer rounded off to 4 significant digits, 35.45 in this case. The mass reported in the periodic table is much more, have more significant digits because the accurate numbers, accurate weights are used than we use in the calculation. If you look at the periodic table, chlorine is 35.4527, which is the atomic number given there. So different elements have different atomic masses, atomic weights based on isotopic distribution. You can calculate if you are given, you can calculate the isotopic mass if you knew the atomic weight. You can calculate if you are given isotopic mass in natural abundances percentage. So this is how we calculated chlorine again. 3497 is the isotopic mass of chlorine 35. 36.97 is isotopic mass of chlorine 37. That two multiplied together gives 75. As a fraction, it is 75.78. As a fraction, chlorine 37 is 0.24. So you can multiply fractions directly without. So in the previous slide, where we divide by 100 is to convert it to a fraction. The fractions are equal to total. So when you multiply isotopic mass in fractional mass, fraction of composition in fraction, so we get the same answer, rounded off to 35.45. Okay, I'm going to stop at this point. Do you have any questions?
No, sir.
You guys, did you sign up the chat box?
I did.
Okay, that's needed because we need to keep track of people who came to the class, okay?
Can you tell me if Tanaya Moore is under there?
Tanya,
Tanaya Moore.
let me see in the chat box whether if I can see you, okay?